Thanks for that introduction and for everyone for coming. Sorry I couldn't be there. So this is the model I put together for the competition. And since I'm going first, I figured I'd go through this, but sounds like Sean already covered this. So we're trying to predict total run size in 2024 for these rivers here. And I guess I only have 10 minutes. So I'll say that, start off saying that I did these predictions entirely during a brief import between two research cruises that I was on, 2 legs of a research cruise that I was on. So I had very limited amount of time. Also, the summarized returns were not available at the time. So I spent about half the time computing total run size from the raw data, as well as run size by age class and escapement and spawners. And I did not have time to search out external data, not because I didn't think it was important, but I just didn't have the time to do that. So I did, however, go and find, obtain the published forecasts for each river if I was able to locate it, which I was in some cases, although it involved a lot of annoying copying and pasting out of PDF files, which took a long time. And then for my evaluation, I ended up splitting all the data sets into a training set, which is before return year 2012, and then a testing set that was 2012 to 2023 that I predicted using the sleep feature out cross-validation, and then the forecast point for 2024. I fit models to log transform data from all variables, but I back transformed them for the evaluation and selected the best model for each river based on mean absolute percent error in this testing set, basically the simulated forecasts. I ended up using a method called empirical dynamic modeling, which I did a longer introduction of in the forecasting workshop, but this is a data-driven nonparametric method that uses time lags to account for missing variables. You can also incorporate additional variables like data from different age classes or covariates. The time lags don't need to be uniform necessarily, and it usually takes this structure of some, whatever it is we're trying to predict, as a function of its lags, and then perhaps the lags of some other variables. And this function is just fit using a nonparametric approach. I ended up fitting it using a Gaussian process regression that my colleague and I developed, focusing mainly on lags up to 8 years in the past, but mostly focused on 1 through 4. The rationale being that most fish return at age 4 in the species. For the Fraser and Bristol Bay systems that had multiple rivers, I used a hierarchical model structure that allows for information sharing across rivers, but doesn't assume the dynamics are identical. I also tried fitting individual models for each river, but at least in terms of percent error, the hierarchical models always outperformed the best individual one, which was interesting, probably because they're more constrained to the mean. And again, because of time limitations, the set of models I considered was not exhaustive, not comprehensive, nor done in a very systematic way. So this is definitely not the best you can do with this approach. I'm quite confident of that. I think there's a lot of room for improvement, and I think including covariates would very likely increase performance, which I didn't have time to look for. So for the Columbia, this is the best model of the handful that I tried that worked the best. So in this case, total run size was a function of run size 1 and 4 years ago, age 2 run size 1 and 2 years ago, and age 3 1 year ago. So these age classes, it's kind of like a non-parametric form of a sibling regression. And then the first 2 terms are kind of capturing, in the case of 4 years ago, the stock-recruit relationship and sort of other sorts of environmental covariance or processes that are going on. So that's kind of the justification for that structure. This is a plot of the observed values and forecasts. So the gray bars here are the observed returns. The blue dots are my leaf feature out simulated forecast. The purple dots are the published forecast that I could find, which was only 3 years. And then the red dot is the 2024 forecast. So at least for the 2 years that I had data, it does seem to be better than the published forecast. Who knows about, probably not for 2024. And these are the percent errors I was getting for presenting, leave one out using all years, and then for the test period. Moving on. Okay, so for the Fraser, I ended up with 2 different hierarchical models. So what they both use time lags of within river run size, different selections of lags. I did find that age 3 last year was actually a really good predictor, but because that was unavailable for 2023, I could not use that to predict 2024, so I had to omit it from the models, which is too bad. These are the rivers that I used or each model for, and I was unable to find existing forecasts by river disaggregated that I needed for comparison, which is also too bad. And so these are similar plots. So again, bars are observed, blue dots are predicted. A lot of these forecasts are not terribly great. These are pretty hard to predict. The error rates are often pretty high, particularly for the future out forecasts. So that just kind of gives you a sense of where those are falling. Bristol Bay ended up having a few more predictors. So I also ended up with 2 hierarchical models. These use a combination of total run size within river, total bay run size, escapement 4 years ago, and then age 3 1 year ago. The second model just used returns last year, escapement 4 years ago, and age 3 last year. And in this one, I was able to find the published forecast, at least for the last 10 years, which is the test period. And so I considered 5 different methods, you could say. One was just to use the published forecast. Then I had 2 of using hierarchical model 1 or hierarchical model 2. And then the 4th and 5th methods were averaging the existing forecast and models 1 and 2. The rationale being that if I couldn't beat the existing forecast, I might as well just use that, and that there might be some advantage to doing some model averaging. So I tried that. I ended up using all 5 methods depending on the river. This is how they ended up getting allocated. These are the error rates for the test period for each of the different methodologies. So at least in some of them, the hierarchical models did better than the existing models. But these are all between about 20 and 40%. So they're all relatively low, and the differences between them are rather subtle. So that's worth pointing out. Okay, here, same plot. We have observed, predicted, published forecasts for each river, percent errors that I was getting for the test period. And at least for the Alagnak and Naknek rivers, the forecast I was getting do seem to be probably noticeably better than the published ones, but the other ones are pretty similar. So that was interesting. So to summarize, Bristol Bay was definitely the most predictable, at least that I found. Fraser River was the least. Some models outperformed the existing forecasts, and I think there's definitely room for improvement. So that's all I got. Interested to see what the other competitors did. So thank you.